Okay, we're back here. It's Monday, March 1st, Physics 1151, continuing chapter 23 with the electric fields. So we're going to calculate electric fields today for continuous distributions of charges. Okay, again, I apologize for the lack of demos. I'm doing this from home, and there aren't many demo opportunities for this subject. So grab a cup of coffee and hang in there today. So where are we heading in the chapter here? Okay, so we talked about the fact that it's much more convenient to discuss interactions between charges in terms of electric fields rather than in terms of forces, especially in applications like chemistry, physics, and in engineering. So what we're trying to do is we're going to try to build up our tool chest. So we calculated before the electric field of a single point charge. And once you know that, you can calculate the electric field due to multiple point charges by just using this solution and applying superposition, right? The electric field is due to a bunch of point charges is the sum of that due to an individual. Today we're going to add our second solution to the tool chest. We're going to calculate the electric field due to a line charge. In other words, for example, a wire or a rod that is a continuous distribution of charge. Then we're going to move on tomorrow to the plane of charge and then to the sphere. And once we know the solutions for these basic configurations, we can build up the solution of more complicated configurations as a sum of the basic building blocks. So recall that we already found that the solution of the electric field due to a point charge Q is that constant. We've been calling it K. You can call it 1 over 4 pi epsilon naught. It's the same number. So it depends on the charge, it depends on the square of the distance, and it goes along the line from the charge to the observation point. Okay? We're going to derive the line charge today, like an infinitely long line charge. So for example, a long wire, what's the electric field produced by a charged wire? And this is the solution we're going to derive. Then we're going to move on to the plane of charge, which describes these electronic components called capacitors pretty well. And then we're going to do the sphere. And recall that since we know the solution for a point charge, if I want to calculate the electric field due to a bunch of point charges, I just find the solution for each charge, which is KQI over RI square. And then I add all of these up like vectors to get the total electric field. Now this is all fine if there's only a finite number of discrete charges, but often in practice objects have a lot of charge. In other words, a continuous charge distribution across them. So you can think of it as almost like an infinite number of little point charges spread out over the object, for example, a rod. And in this case, we can't sum them up, but rather we need to apply the technique of integration. Remember, where we take the limit as each little charge element approaches zero, and you have an infinite number of charges, and we need to do an integral over this charge distribution to get the total field, and that's where we're going today. So when you have these objects that have continuous charge distributions, so let's take for example a rod here or a wire. And suppose the wire has a total charge Q, big Q. We're going to use big Q for the total charge. And suppose that the wire or the rod has a length L. Okay? We can take this rod to have a linear charge density, which is charge divided by length. And we're going to call that lambda. And lambda is equal to the total charge over the total length. if this charge is uniformly distributed along the wire. Okay, so in this little element of length delta L, we will have an amount of charge delta Q, okay, such that the density is Q over L. So what we're going to do in these coming examples in anything with continuous distributions is we are going to break up this charge into these little elements, delta Q. We're going to find the electric field contribution due to each little element, and then we're going to add them all the way up. In other words, we're going to do an integral along the length of the rod or the wire. So here we go. Okay, so suppose that, let's look at what these densities are. Okay, suppose you have a wire or something that's one-dimensional. So in other words, it's very thin in the perpendicular direction. And so we can assume it's roughly one-dimensional. And so if the wire has a length L and a total charge Q, then we can define this charge density, which is the charge per unit length. In other words, coulombs per meter is the charge density units. And that means there's an amount delta Q of charge in this length delta L, and the density is delta Q over delta L is lambda. Now we can write this as dQ, which is the element of charge in this element delta L, is the charge per length times the length. So charge is the density of charge times the length. And that's the amount of charge in this length delta L. Okay. So 2 dimensions, now instead of length, we're dealing with area. So for example, a sheet of charge, and we can define this surface charge density, which they call eta. It's a squiggly N. It's a Greek N. And that's the charge per area, which is total charge over the area of the surface. Or for infinitesimal charge in an infinitesimal area dA, the charge per area would be delta Q over delta A. And similarly, we can write this in terms of the charge in this little area. Delta Q is equal to the charge per area times the area, or eta times delta A. And so this is expressing dQ in terms of a surface charge density. Okay, where this now has units, eta has units of coulombs per meter square. When we get to electric fields of 3-dimensional objects, we need to deal with charge per volume, and we define this volume charge density, which they call rho. It's a Greek-looking P, and that's equal to the charge per volume, or delta Q over delta V. And similarly, we can write that this incremental amount of charge delta Q is the charge per volume times the volume. Okay, so instead of Q in our point charge equations, we're going to use this delta Q as the contribution from a given element, and then we're going to integrate over the whole volume, over the whole surface, or over the whole line, the contributions to get the total electric field. Okay. So let's start off with an example in 1 dimension, since that's easier than 2 dimensions. So let's consider this charged wire. And the wire has a length L, and it has a total charge Q, and so the charge density is the charge per length, which is Q, divided by L, and that's the charge per length along the wire. And so what we want to do in this example is we're going to calculate the electric field at some distance, the author calls this R, from the center of the wire along this axis perpendicular to the wire. So to some observation point P. So what we're going to do is we're going to break this wire up into little segments of length delta L, having a charge delta Q, and we're going to use the point charge equation for this little element to calculate the electric field contribution for this element. Then we're going to go up to the next element, and we're going to calculate the equation for the electric field due to that, and we're going to sum them all up. Okay. So before we do that, there's certain cases where symmetry can help us to help make the problem simpler. And in this problem, if we look here and we draw the electric field, say from this point below the center and an equidistant point above the center, we see that the electric fields due to both components, which are along the line of this little element of charge and pointing away, since it's positive, we see that these electric fields, the components along the y direction, cancel in pairs because both elements are the same distance from point P and they have the same magnitude of charge. So the y components are going to cancel in pairs. And you can go up one a little element, and the contribution from this element will cancel the contribution from this along the x direction. And when you add all of these up, all of the x components of each incremental electric field element are going to cancel in pairs. And so we're only left with the contributions along the x direction. Okay. So we don't even need to deal with the y components of the electric field because we know they're going to be zero. They're going to cancel in pairs. Okay. So let's move on to solving this. So each little element in each little element delta y here, there will be an amount of charge delta Q is charge per length lambda times the length delta y. And each of these points will be at a distance Ri from point P. So what we're going to do is the contribution delta EI from element I is equal to the constant K, or 1 over 4 pi epsilon naught if you prefer, times the amount of charge delta Qi divided by the distance Ri square. And this is along the distance where the unit vector Ri specifies that it's the direction is along the line from this increment of charge to point P. So in this case, Ri would point along this direction. Okay. Now we need to break Ri up into its components along the x and y directions. Okay, so this Ri, the unit vector along this direction, would have a component cosine of theta along the x direction and a component sine of theta along the y direction for points above the axis, and for points below the axis it would have cosine of theta along the x direction and sine of theta along the y direction. And we denote the x and the y directions using I hat and j hat, these unit vectors that you used in Physics 1150. The I hat is just a vector of magnitude 1 along the x direction. J hat is along the y direction. So these just specify the directions of the two components. Okay? So since we know the y components cancel in pairs, we don't need to worry about them, and we only need to deal with the x component, which is cosine of theta. So we plug in cosine of theta here along the I direction. Okay. Now dqi is equal to the charge per length times delta y, so we're going to plug that in, and then the distance, little ri, from charge element I to point P is this distance, which is equal to x squared plus y squared. Okay, so that's the distance from the charge element to point P. Now the author uses r for this distance, this perpendicular distance along the x-axis to point P. I'm going to use x because it's along the x direction. And then at the end, when we're all done deriving this, we can substitute r for x just to be consistent with the author. But I think using a small x here is advantageous so that we remember that it is the distance along the x direction, as opposed to this ri here, which is along the distance from the charge to the point. Okay? So in this case, ri, the distance from each little element to point P, is equal to y squared plus x squared to the 1/2. So let's plug all of these in. We get that the x component of the electric field is the integral from y is negative L over 2 to y is L over 2. And k is the constant. Lambda dy is dq. Delta q is charge per length times the length. The square of the distance is in the denominator, right? It goes as ri squared, and ri squared is y squared plus x squared. And then we have this cosine of theta because, remember, we're only adding up the x components to get the total field, because we know that the y components are going to cancel in pairs. So what we're solving for is the non-zero component of E. The net field is along the x direction. Okay, so there's one more problem here, is we have this cosine of theta here, but we're doing an integral over y. Okay, so we need to express cosine of theta in terms of our coordinates. And so we can do that because if theta is this angle, cosine of theta is equal to adjacent, which is x, over hypotenuse, which is ri. And ri is just x squared plus y squared to the 1/2. So we're going to substitute that in for cosine of theta, and now we're able to perform the integration. Okay. And notice that we now in the denominator have x squared plus y squared to the 3/2 power, because it was to the first power, and then when we put in cosine, it's another 1/2 power. So it goes as x squared plus y squared to the 3/2. Okay. Now, lambda is a constant, k is a constant, x is a constant, so we can pull all of these out of the integral, but we're still left with kind of messy looking integral here. Okay, we're integrating over y, and we have a constant square plus y squared to the 3/2. Okay. Fortunately, there are tables of integrals that we can go to if it's been a while since we've solved these. And so you can go to Google and you can look up in a table of integrals, and you can get that this integral is given by y over x squared times this to the 1/2. Okay, so we plug that in. We evaluate at the limits L over 2 to y is negative L over 2 to L over 2. And we get this as our electric field. Okay. So we have now solved for the electric field, the x component of the electric field, at some distance x, author calls r, from the center of a wire. So the field points perpendicular to the wire in the x direction. So this is our end result. So it depends on the total charge Q. It also depends on the distance and on the length. So this is kind of a complicated looking formula. It's not particularly insightful. So let's look at some limiting cases that often apply in practice. So the first case, let's assume that the distance x, or r as the author calls it, the perpendicular distance from the center, let's assume that that's a lot longer than the length of the wire. So in other words, we're far away from the wire. Okay, so x squared will be much, much larger than L over 2 squared. And let's suppose it's so much larger that in this denominator, we can ignore L over 2 squared in comparison to x squared. So we're just going to ignore this. And so this denominator in this term here becomes x times x squared to the 1/2, which is another x. And we get that the electric field is kq over x squared. Okay? And that's the same field as a point charge. I put an absolute value here because we derive this for a positive charge, but it also would apply for the same magnitude of negative charge. The electric field would just point toward the wire instead of away, but the magnitude would be the same. Okay? And that's why there's that absolute value here. So what this says is that if we're very, very far away from the wire, it almost looks like a point charge to us. This dimension L it becomes indiscernible. So we can't, the electric field is the same as if all of this charge Q were at the center instead of being distributed if we're very far away. Let's look at another case which is perhaps more interesting. Let's assume that L is very long and it's much larger than the distance from the wire where we're evaluating. In other words, let's move this point P up closer to the wire. Okay? And in this case, we have x squared is much less than L over 2 squared, and so we can ignore x squared in the denominator. And if we ignore that and we solve it, we get that the electric field, this whole denominator becomes x times L over 2, and Q over L, charge per length, is just the charge density divided by x. And so this is an electric field of a long wire, or in other words, the length of the wire is a lot larger than the distance at which we're evaluating from the wire, the field. So in other words, it's approximating an infinite wire. So this is our example here where the author again uses absolute value for the charge density, and then it's away from the wire. It's away from the wire if it's a positive charge, the electric field, and it points toward the wire if it's a negative. Okay, so we derive this for a positive charge distribution, but now we're just generalizing the result in case the charge could be negative, because you're going to get the same magnitude. It's just it's going to point in the opposite direction. So there's no point in deriving this all over again for a negative charge. So we're just going to put an absolute value here so that it can apply to both cases. So this is the main result here. This result here, you should be able to derive this on an exam or a quiz. But as far as using it, it's kind of clunky to use. It's not very intuitive. And in many cases, we're going to be dealing with a wire that's much longer than the distance from the wire where we're evaluating the electric field from. In other words, L is much longer than what we called x, the distance along the x direction, or the author calls r. Okay, so now that we're done deriving this, we can replace x by r if you want. So r is the perpendicular distance from the wire to where we're evaluating the field. Okay? And so what do we see? We see that the electric field strength depends on the charge density. In other words, how much charge per length is piled up in this rod. Okay, that makes sense, right? More charge, stronger field. And it also decreases as 1 over r, where r, or what we call x, is the distance from the wire. Okay. Interesting thing about this is it's different from a point charge, right? Point charge, the electric field goes as 1 over r squared. This line charge, it only goes as 1 over r. Okay, so the electric field decreases more slowly as you move away from a wire, since it only goes as 1 over r, than it does for a point charge, which goes as 1 over r squared. So now we've added our second solution here. We go back. Here's our second solution. We found the solution for a point charge. We now know the electric field for a long wire. Okay, so we put that in the tool chest. So what happens, in other words, how much does the by what factor does the electric field strength change if we double our distance from the wire? So let's suppose we start off at a distance r from the wire, and let's suppose we go out to 2r. So we double our distance from the wire. What's the electric field strength out here? Okay, how much weaker is it going to be than when we were at some distance r? Okay. And this is easy. We replace r by 2r, and the electric field is only half of what it was at a distance r. So every time we double the distance from the wire, our electric field is half as strong as it used to be. So let's do a class exercise here. So suppose we're at some distance p, some distance from the rod, and we want to know what the effect is going to be on the electric field if we change each of these variables. Okay, so let's suppose we make the rod longer, but we don't change the amount of charge. Okay, what's that going to do to the electric field? Okay, well, the amount of charge is the same, the length is longer, so the charge per length is less. Okay, that means the electric field is going to be less. And so this making the rod longer and keeping the charge constant is going to reduce the charge density, and that's going to make the electric field smaller at this point. Okay, what about part B here? Okay, suppose that we keep the amount of charge Q the same, but the length of the rod, or the charged rod, is shorter. Well, that means that the charge density, charge per length, is greater, right? Same amount of charge, shorter length, greater charge density. That is going to increase the strength of the electric field. Okay, so B will increase it. What about C? Make the rod wider without changing the charge. Okay, well, in this case, the charge density will decrease, so that will not increase the field strength. Making the rod narrower without changing the charge will make the density greater, charge density. That will increase it. Adding charge to the rod, well, then the charge per length increases, so the field will be stronger. Removing charge from the rod, charge per length will be smaller, field will be smaller. So what about if we move the dot further from the rod? Okay, well, increasing the distance from the rod will make the electric field smaller, right? Bigger R, smaller field. Making the dot closer to the rod. As we get closer to the rod, R is smaller, electric field is bigger. Okay, so you should be able to use this solution here for the electric field due to a long wire or a long line of charge, and you should be able to examine the effect of varying these variables on the field. Okay, so this could be like a multiple choice type of question on an exam. Okay, now that we've derived the equation for the electric field for a line charge, and that was one of our 4 fundamental solutions. Okay, that was an important one. Put a star next to that one. The next thing I want to do is I want to calculate the electric field due to a charge charged ring. Okay, this isn't one of our four quote fundamental solutions, but it provides another example with calculating the electric field due to a continuous charge distribution. Okay, so let's assume that we have a ring in that all points on the ring are some distance big R from this origin of our coordinate system. So it's a ring of radius R. And let's suppose that the ring has a uniform charge, total charge Q on it. And let's assume also that the ring is thin, and so that all points on the ring are at the same distance, big R, from the center. So then you can think of it, since it's very thin, it's a one-dimensional. You can think of it as a line charge where the length of the wire is 2 pi r and it's wrapped into a circle. So all we've done is we've taken our straight line charge before and we've made it into a circle of radius r. So in this case, the linear charge density, which is the charge per length, is the total charge over the total length, which is big Q divided by 2 pi r. Okay, so this is a ring of charge density lambda is Q over 2 pi r. Now, we can solve this, and in this case, in general, you're going to have three components for the electric field, right? A z part, an x part, and a y part. So we're trying to calculate the field along the axis here from the center, right? A line right through the center and perpendicular to the ring at some distance z away from the charge here, from the ring. Okay. And so before we start calculating all three components, let's see if we can use symmetry to simplify the problem. Okay. And if we do that, since we're evaluating our electric field at the center here, we see that for any point that's above along the positive y-axis, so at any point at the top of the ring and any point at the bottom of the ring, when you add their components, their contributions to the electric field, the components along the y direction are going to cancel, right? Here's the bottom of the ring, and that electric field will point up. That has a component in the plus y direction, and this component of charge right here at the top has an electric field, and its y component is in the negative direction. Okay, and there's the same amount of charge on the top as on the bottom, and they're both the same distance from point P, and so their y components are going to cancel. Okay, but their z components are not going to. They're going to add. Okay, so you can go around for any 2 points that are symmetric on either side of the ring, and you'll see that their y components of the field will cancel at this point P. Okay. Similarly, we could take 2 points along the x-axis, along the horizontal of this ring, say this point here and this point here, and if you drew their electric fields, the components along the x direction would cancel in pairs, but the components along z would not. And you can go around for every 2 pairs that are opposite each other on the ring, and their x components cancel. Okay, so again, because of symmetry in this problem, there is going to be no y component of the field, and there's also going to be no z or x component of the field at P. So again, symmetry, we lucked out here. We only have to calculate the z component of the field, so the net field will be in the z direction. Okay, so the x and the y, there is no ex, there is no ey, because all of the little contributions cancel in pairs. Okay. So once again, the z component of the field is equal to the field's magnitude, EI. This is the contribution from segment I. It's EI times the cosine of theta I. So that's what we're trying to find here, is that contribution from element I, and then we're going to integrate around the ring to get the total electric field produced by all of the charges on this charged ring. Okay. So we go back to our equation here. Remember, we have, here's dE, this element from this field due to element I, is equal to K times dqi, remember the little element of charge delta qi here, divided by the square of this distance ri from point P to this element of charge. And then that's multiplied by cosine of theta because we're trying to find the z component. We know that the x and the y components are 0 due to symmetry. So this is what we're trying to solve. Okay. So once again, we luck out because all of the points on the ring are the same distance ri from point P. And that's given by r squared plus z squared to the 1/2. Okay, it's just Pythagorean theorem. Little ri squared is big R squared plus z squared. And so all of these points are located at the same distance, little ri, from point P. And so we're going to substitute that in here. And cosine of theta is the same for all because all of the points are at the same height or the same radial distance from the center. And so we can use trigonometry here. Cosine of theta is equal to adjacent, which is z, divided by hypotenuse, which is little ri. And so cosine of theta is equal to z over r squared plus z squared to the 1/2. So now we can plug that in for cosine of theta, and we can plug this expression in for ri squared. And then we need to know what delta qi is. Well, that's equal to the charge per length times this little element of length. If you remember from polar coordinates, this arc length, delta L, is equal to the radius r times the change in the angle, or delta phi. And so delta L dl is equal to r times delta phi, where this is this polar angle from the x-axis. Okay, so now we plug that in for dq. We plug this expression in for ri squared. We plug this in from cosine of theta. And now we have the contribution of the electric field from from this little element I of charge. Okay. Now we've got to integrate this. So that means integrating this from phi is 0 along the x-axis to phi is 360 degrees, which means one time around. So in other words, phi is 0 to 2 pi. We're going to integrate this contributions to the electric field, so superposition gives us the total. Okay. Now fortunately this ends up being a really easy integral, so it's not as bad as it looks. So we plug all this in, and since we're integrating or summing up the contributions from phi is 0 along the x-axis, here's 90 degrees, here's 180, 270, 360, or 2 pi. Since we're integrating over phi, and none of these other variables depend on phi, right? K is a constant, lambda is a constant, r is a constant, z is a constant. We can pull all of this stuff but d phi out of the integral, and we're left with a really easy integral, right? Integral of d phi is just phi evaluated at the endpoints, which is 2 pi minus 0, or 2 pi. So this integral looked a lot scarier than it was, okay? It's only 2 pi, and now we've got our expression for the electric field along the z direction. Now we could either leave it in terms of the charge density, or the author, in the spirit of confusion, decides to switch back to charge q, and so q is equal, the charge is the charge per length times the length of the ring, which is 2 pi r, and so we can write 2 pi r times lambda is q, and that's another way of expressing the electric field. It really doesn't matter which one of these two ways you do it. I'm just being consistent here with the author. So this is the equation here for the electric field at some distance z from the center of the ring. Okay, perpendicular to the ring. Okay, so Let's look and see. Let's check a limiting case here to see if we messed up on our formula. So we know that if Z gets very, very large, so suppose we walk way far away from the ring, this ring should look as if all the charge is at the center. It should look like a point charge. So let's check this. If we make Z so much larger than the radius R, then in the denominator, R squared plus Z squared is roughly Z squared. So we can neglect the R squared, and we get Z squared to the 3/2 power is Z cubed. One of the Z's cancels out the numerator, and we're left with the case the electric field is KQ over Z squared, and that's just a point charge. So that gives us confidence that we didn't screw up in our derivation. So these limiting cases are always good to look at. So this is the electric field on some distance of the axis due to a ring of charge. Okay, I would not place this on the same importance as it's just a line charge of length L, but it's another application of how to do integration and when you have a continuous distribution of charge. And especially for those of you who go on and take more physics like electricity and magnetism,